Hello, I am Dr. D.S. Kushan applying for a postdoctoral fellow position at ATDC. My research focuses on developing an AI-assisted welding machine with emphasis on mechanical systems integrated closely with your power electronics team. Let's explore this vision. Modern manufacturing demands intelligent welding machines that adapt in real time to diverse materials and geometries. My research has four objectives. First, develop the mechanical core, a multi-axis robotic platform, thermal management, precision actuators, and a rigid frame. Second, integrate AI-driven adaptive control using real-time sensor feedback. Third, collaborate closely with power electronics on high-power supplies, real-time interfaces, and sensor conditioning. Fourth, deliver a validated platform for consistent, high-quality welds. What's unique? We are not retrofitting AI into existing machines. We are designing mechanical and electrical systems from first principles to work in concert under intelligent control. Four core mechanical subsystems. A 6 to 7 degree of freedom robotic platform for precise torch positioning on complex 3D workpieces, sub-millimeter accuracy. Advanced thermal management, cooling channels, copper heat sinks, thermal shielding to sustain high power operation without degradation. Precision actuators, servo and stepper motors with real-time feedback controlling torch travel, arc length, wire feed, and shielding gas. Millisecond responsiveness, a structurally rigid frame minimizing vibrations that disrupt the arc, yet designed to handle dynamic welding forces safely. Real-time sensor data, voltage, current, arc length, thermal imagery feeds into a neural network. The AI predicts defects before they form: porosity, incomplete fusion, spatter. It adjusts torch position and travel speed proactively. Machine learning models optimize torch trajectories for specific materials. Mild steel welds differently than stainless or aluminum. Our AI learns and adapts. The control loop runs in milliseconds: sense, predict, adjust. This control loop adaptive approach is what enables consistent, high quality welds across diverse scenarios. 4 critical engineering challenges. Arc stability. Vibrations disrupt the electrical arc. We solve this through rigidity analysis, vibration damping, and compliant fixtures. Thermal cycling. The torch experiences extreme temperature swings. Advanced cooling and thermal shielding manage this, validated through detailed thermal profiling. Dynamic responsiveness. AI commands adjustments, mechanical inertia resists. We need high bandwidth actuators and low latency systems. Milliseconds matter. Sensor integration. Thermocouples, pressure transducers, vision systems coexist with a high current welding environment. Careful electromagnetic shielding and sensor placement are critical. 4 areas of essential collaboration. High power supplies. Regulated DC-AC at 200-400 amperes with tight ripple control. Power quality directly affects arc stability. Real-time communication. CAN bus or EtherCAT between power electronics and mechanical control. Latency breaks the adaptive loop. Sensor signal conditioning. Joint effort on amplification, filtering, and digitization. Clean signals enable good AI decisions. Thermal coordination. Unified system, wide thermal strategy, not siloed mechanical and electrical cooling. This collaboration is fundamental to success. Structural analysis. FEA validates frame rigidity, stress distribution, and dynamic modal behavior. Actuator performance. Servo and stepper motors tested for repeatability, settling time, and bandwidth must meet AI control demands. Thermal testing. Sustained high power welding with temperature profiling across the system validates our cooling strategy. Weld quality evaluation, metallography, tensile testing, visual inspection correlating mechanical performance to defects. Good mechanics produce good welds. 24 months, 4 integrated phases. Phase 1, months 1 to 4. Mechanical design, CAD, FEA, validation, component procurement. Phase 2, months 5 to 8. Prototype assembly, commissioning, actuator tuning, sensor integration. Phase 3, months 9 to 16. AI model development in parallel, power electronics integration, closed loop testing on test panels. Phase 4, months 17 to 24, full system validation on industrial materials, steel, stainless, aluminum, with weld quality documentation and production optimization. Clear milestones, achievable timeline. A prototype AI-assisted welding system demonstrating adaptive control and measurable defect reduction compared to conventional machines. Validated mechanical subsystems ready for scaled manufacturing and industrial deployment. Published research and patents advancing intelligent welding automation. Industry partnerships and a commercialization pathway for automotive, aerospace, and heavy manufacturing. This postdoctoral research bridges mechanical engineering, power electronics, and AI. We create a transformative welding platform for Industry 4.0, intelligent, adaptive, consistent, scalable. Thank you. I welcome collaboration and questions.